Hello, this project investigates which climate and vegetation factors best explain wildfire ignitions in California during 2024. Instead of focusing on burn area or fire severity, we focus specifically on ignition events, since ignition is the earliest and most preventable stage of wildfire activity. We combine ignition and non-ignition events with vegetation and climate data to understand not just when fires happen, but under what environmental conditions ignitions are more likely to occur. Our central question is, among climate and vegetation variables, which factors are the most strongest predictors of wildfire ignitions in California in 2024? As lifelong California residents, we've observed the increasing frequency of wildfires and wanted to move beyond anecdotal explanations to quantify which environmental drivers matter most, especially under current climate conditions. Prior research consistently shows that wildfire risk is shaped by the interaction of climate, fuels, and human activity, with recent studies emphasizing the growing role of atmospheric dryness and temperature due to climate change. Work by Kalashnikov highlights vapor pressure deficit and fuel moisture as key ignition drivers, while Jiang et al. Shows that combining climate and vegetation improves predictive performance. Our project builds on this literature by focusing specifically on ignition events in a recent year and by explicitly comparing ignition to non-ignition conditions. We've hypothesized that higher temperatures, higher vapor pressure deficit, lower fuel moisture, and shrub-dominated vegetation types such as chaparral would be most positively associated with wildfire ignition. Our null hypothesis is that climate and vegetation variables are not significantly associated with ignition, while the alternative hypothesis is that one of these variables meaningfully contributes to the likelihood of ignition. We use 4 datasets: CAL FIRE ignition records, randomly generated non-ignition events, land fire vegetation data, and GridMet climate data. Ignition and non-ignition events provide an labeled outcome variable, vegetation data describe fuel structure and composition, and climate data capture daily environmental conditions. After cleaning and merging, the final dataset includes 2,423 events with 4 vegetation variables and 14 climate variables per event. For data wrangling, significant pre-processing was required to align spatial and temporal information across datasets. Ignition and non-ignition events were merged, vegetation and climate variables were added via APIs, and vegetation variables were categorized into interpretal classes such as fuel model, vegetation height, cover, and type. This step was crucial for ensuring consistent comparisons across ignition and non-ignition events. We begin EDA by examining where and when ignitions occur. Spatial maps show that ignition events are clustered in certain regions of California, but spatial location alone does not explain ignition risk. Temporarily, ignition events peak strongly between May and September, aligning with California's hottest and driest months. This immediately signals seasonality as a confounder, motivating a deeper look at the underlying climate variables driving this pattern. Vegetation EDA shows the non-vegetated and low height categories dominate the dataset. Raw ignition counts are highest in agriculture and urban areas. But once normalized, no vegetation category shows a simple monotonic relationship with ignition. Vegetation height and cover also fail to reveal a consistent single pattern. This suggests vegetation alone is not a standalone predictor and motivates the use of machine learning to detect subtler interactions. In contrast, climate variables show a strong structure. Correlation analysis reveals tight relationships between temperature, vapor pressure deficit, evapotranspiration, burning index, and fuel moisture. Box plots comparing ignition and non-ignition events show that ignitions consistently occur under hotter, drier conditions with lower fuel moisture. This reinforces our hypothesis that climate conditions drive ignition risk, and that these effects likely act jointly rather than just independently. The EDA showed two key insights. Vegetational variables lack simple explanatory power, and climate variables are highly interrelated and jointly with ignition. Because no single variable explains the ignition on its own, we move to machine learning model to model multivariate relationships. Geographic variables and explicit seasonal variables were removed to prevent the model from learning where or when fires happen instead of why they happen. We trained two models, logistic regression and random forest classifier. Logistic regression provides interpretability through coefficients, while random forest captures nonlinear interactions. Climate variables are standardized, vegetation variables are one-hot encoded, and stratified train test splits preserve the class balance. Both models are trained on the same feature set to enable direct comparison. Both models perform well above chance. Random forest achieves higher overall accuracy and RUCAUC curve, while the logistic regression achieves a higher recall for ignition events, which is important for minimizing missed ignitions. Confusion matrices show that both models struggle with false positives and false negatives, reflecting the complexity of ignition processes and the absence of human behavior variables. Feature importance and coefficients show strong agreement with EDA. Temperature, vapor pressure deficit, evapotranspiration, burning index, and fuel moisture are the most influential predictors. Vegetation variables appear but play a secondary role. Visualizations in climate space show that events clustering under hot, dry conditions, which confirm that climate is dominant ignition driver. This project uses public, non-personal identifiable information, environmental data, and poses minimal privacy risk. We acknowledge biases from spatial aggregation, missing human factors, and class imbalance. We explicitly avoid causal claims and frame results as probabilistic. The analysis is reproducible and transparent, and results are communicated with clear limitations to prevent misuse. Overall, this process and project finds that wildfire ignition in California is strongly structured by climate conditions and seasonally driven dryness, while vegetation plays a weaker indirect role. Ignition risk increases under combinations of high temperature, high atmospheric dryness, and low fuel moisture, rather than just from vegetation type alone. While the models capture meaningful environmental signals, they also highlight the use and the importance of unobserved human and fine-scale factors. Thank you for watching.